Okay, so the final talk in this session, Daniele Nantes, who tells us about type non-determinism the eager way.
Thank you. Yeah, so this is a joint work with my colleagues, Joe, who's there, Bas, who is in Germany now, and Jorge from the University of Groningen. So I say that this research is part of my old life before I started working with Filipa. So we managed to join well the knowledges because my background was in lambda calculus, and Jorge worked a lot with the pi calculus, and then Joe arrived and he put Joe in the middle to learn both. So we have to speak two languages. We have to speak the language of lambda calculus and the language of the pi calculus for this work. So this work is about the delicate relationship between non-determinism and resource management. And we are going to explore how the properties are maintained between the two languages. But we want to have the pi calculus typed with session types and the lambda calculus typed with the intersection types. So for the ones who doesn't know, for us a session type describes a protocol used by communication processes. So for instance, if you have that assignment, X has type A, means that X should conform to the protocol specified by the session type A. So what are our goals, or were when we started working on this? We wanted to design programming languages. Like we wanted to design an expressive pi calculus that was session typed, and it had nice properties such as non-determinism, that you could control how the resources were used, and that you could see when you were failing. So we wanted to have a very nice pi calculus, and it's a big work to say that we want to do that. So we started in parts. So first we studied confluent non-determinism, and then we started studying non-confluent non-determinism, but with a different semantics. And this work is about confluent non-determinism with eager semantics. And you're going to see why. So we are going to present a lambda calculus with standard non-confluent non-deterministic choice, which has failure behavior, and it follows a eager semantics. We are also going to present a session type system, which ensures type preservation and deadlock freedom. That means that process never gets stuck for us. If it's typed, it doesn't get stuck. Okay, and then let's move to another language. On the lambda calculus side, we are going to work with the intersection type resource lambda calculus. It's non-determinism, non-deterministic fetching of resources from bags. And then we have to speak both languages to know how to move properties from one to the other. So we have a translation between these two types, and then we prove that we have some sort of loose correctness, which means type preservation and operational correspondence. So we have a dynamic correspondence between these two languages. I'm going to unpack many of the things that I said, and then let's start. So first of all, non-determinism is when reductions may introduce different behaviors. So for instance, if we know that P1 reduces to Q1, here for their processes, P2 reduces to Q2, then P1 plus P2, the plus is the choice operator. If you reduce first the P1, you are going to have a choice between Q1 plus P2, right? And then on the other hand, if you choose the P2, you are going to have that process there. Let me see, where is the pointer? Where is the pointer? I don't know, anyway. So, but then, if you look at that process there, you can reduce P2, right? So you are going to end up with Q1 plus Q2, and then here the same. So in the end, they are going to end in the same position. So this is an example of a confluent behavior. But this is not the standard non-determinism, which is non-confluent. So usually if you have a choice, you pick one and then you discard the other, okay? So here I have two possible behaviors and it is not confluent. So it's clear that it's not confluent. So I don't need to address how important it is to deal with the non-determinism, but it's used in specifications of distributed protocols. And then their commitment is important. So you need to choose what you're going to do. And then once you choose, you chose, so that's it. And it's used in verification frameworks that are based on algebraic processes, such as this MCR-CRL2. And then it's also relevant in the functional calculi. One of the well-known framework is this work by Ligori-Paperno, but it's untyped, non-deterministic lambda calculus. Actually, the work on non-determinism in lambda calculus dates from the 90s, I think, with Gerard Boudal, and it's like a very old work. And then people keep working and extending the expressivity of the lambda calculus. So we explored many variations of the lambda calculus to build this work. So what we found out is that the relation between non-confluence, non-determinism is problematic when you want to also control resource. You have to balance what you're going to do. So this is the main difficulty. So the calculus that we are going to present is S-pi exclamation mark. And the lambda calculus I'm going to call lambda C. And then we are going to present this translation. So to start, I have a new operator that's my non-deterministic construct. It represents denotes the non-deterministic choice between P and Q. If one branch can perform synchronization, the other branch may discard it. Okay, so you choose between one and the other. So in the untyped pi calculus, this is how the usual non-determinism occurs. So there you have a choice between the process send Z and then behaves as P1 or Pn1. This is communicating with another process that receives something in Y, in X, continue as P2, or does whatever M2 says. And then if you see, it's discarding M1 and it's discarding M2 because I chose one and then I discarded the other processes. But the problem is we want to type, and this is not type, and we want to type with session types. And it's very hard to maintain the Curry-Howard isomorphism if you don't have confluence. Okay, actually, it's but so we had to do some magic to make it work. So just to give you an example, so these are two processes for server and non-deterministic client. So the move server expects to receive a title of a movie, and then it gives you two options. Either you can buy or you can just pick. And then if you choose buy, for instance, then you have another two options that you can pay by card or by cash. So, and then the client is going to say, send to the server, I want to watch the Barbie movie. And then the client has three options. Either the client is going to choose to buy the movie in cash or in card, or just pick. Okay, so the movie service gives two options to start, and then the client side has to choose between one of these choices. Okay, so what's going to happen? This is just by example how our semantics work. So for instance, if I had one of the possible reductions is going to be the blue one, which is my client chose just to pick. And then it communicates with this process, and you see the other possibilities just died. See, so it committed to the pick. Another behavior is this one, which chose just the buy with card, and then discarded the other possibilities, and so on. Okay, so this is our process calculus. So it's basically the normal pi calculus, but here I have non-deterministic choice. I have these two constructors, that is, this asks if this says, I need confirmation that I have a name X to continue, and the other one says, this confirms the availability of the resource that says I need resource on it. So, and this is when you say, I don't have resource on this. Okay, so this is the extension that we have on our calculus. So, okay, before I give you the semantics, the eager semantics, I need to give you some technical details. So we have this kind of context, they are called non-deterministic contexts. And then we need to have another operator that collapses the rest, okay? So this is the commitment of a non-deterministic context. So if you look at this process, the last one, you see if you have something, a choice between a process, a non-deterministic choice between a process P and the rest, you choose P, that brackets, and it's just to say collapse all the other things that you have there, okay? So this is the horrible, I know, but let's just choose one. So this is part of our eager semantics. So for instance, this is saying, well, among my deterministic choices, I have this process that aims to send a name Y through channel X and then behave as parallel with Q. And then this is in parallel with another process that may be lots of non-deterministic choices, but one of them is what's happening. Allow or deny? It's a choice. Oh, no, do we close the okay. So we can make a next example like with Zoom, allow or deny, not a client server. So what happened here is I chose to communicate this send with this receive, and then I'm going to collapse all the other things that I had in the non-deterministic choices, and I'm going to collapse all the other things, and I'm just going to go with this branch that I chose, okay? And the other rules are basically the same. Yes, this is the most interesting one. Yes. So now I want to type it. So these are the types in linear logic. So this is typing a channel that first send a name of type A and then behave as B. That's what it means. This is expecting to receive a name of type A and then behave as B. This types a client and this types a server, for instance. And this is one is choice and the other one is selection, and then we have lots of typing rules for non-determinism. So here, if you want to choose between P and Q, you need to be able to type P and you need to be able to type Q, okay? But then you can choose between them. This says if you are confirming the availability of X, you need to confirm, and then P, if your X has this type, this is to the type of non. Yes. It's also failure because if you need, for instance here, if you need some name available, but when you communicate with that non, you don't have a name available. So you're going to fail. Our calculus is expressive to say, no, it's not, it fails. So now, I made it 15 minutes for the first language. Now let's change the dialect, let's change the language. So why do we want to talk about lambda calculus? You are designing a language and you can think that it might be too artificial. too forced. It has all the nice properties, but I was going to use that, right? So what happened is we managed to make a translation from a language that exists in the functional calculus into that. So it's not like a random language that we defined, okay? So this calculus is based, this lambda calculus is based in a lot of studies on the resource lambda calculus by Michele Pagani, and then also atomic lambda calculus from Whelan, and also lambda calculus with multiplicities. And then, I mean, these are all calculus that exist for many, many years. And Joe made the great job of extracting the nice bits of each and building this. It's not very different from the things that exist. We have a variable that you have to say if this variable is going to receive linear resources or unrestricted resources. So if I annotate this variable, the occurrence of a variable with a label like this, it says it can only be substituted by a linear resource. Okay, if I annotate a variable with a number, it means I need to consume an unrestricted resource. We are going to annotate occurrences saying which kind of resource we're expecting. That's what we're going to have. And then we have to have three different kinds of explicit substitutions. Why? This is because you start with resources that have linear and unrestricted. And then the B means that you have linear and unrestricted resources. Should I allow?
I have just sent a message to Sam said that he's not the one who's.
Okay.
Sorry.
No, it's fine. And then what we are going to do is we are going to define grain. So we are going to split the explicit substitutions in an explicit substitution of linear resources and another one with unrestricted resources. And we are going to work with these two different kinds of resources in a different way, okay? So this is how a lambda term looks like. So this is basically, if you think about lambda calculus, the normal one, this is lambda x, 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 okay? So just to go back, so I have lambda abstraction normally, the normal, but what's different here is the application. So you're going to apply a term to a bag. So you have a bag, imagine that you have a bag, many lambda terms inside, okay? Some of these lambda terms that are inside can be used only once. Some of the lambda terms that are inside can be used as many times as well. Okay, so this is like the resource lambda calculus propaganda. So here, all my variables, when I put this sharing construct here, so here I said it's lambda x, x, x. So this is a lambda of an application of a variable to a bag. Okay, so this is just to show how you look at this. And if I use the same variable, when I do an application, I'm going to replace the same variable in other places, right? When you do the substitution, right? And I cannot do that because each linear resource can be used only once. So what we do this atomization, which is we rename each occurrence with a new variable, and then we annotate that all these variables here are renamings of x, okay? So what happens when I apply? So this is a lambda abstraction applied to a bag with 3 resources, okay? So now I have a choice. What can I choose? I have a bag. A bag is for us, this linear bag is a set of lambda terms, okay? So I can choose to apply to replace x1 by fail, or for the first step, that's what I did. But I could have chosen, instead of choosing fail, I could have chosen y, for instance. So I have three options for the first step, okay? So these are the 3 choices. Okay. I didn't use the colors. So that's the identity lambda term for us. Yes, so this is a type system for our, these are the reduction rules, yes. So see, if you have a beta reduction, lambda x applied to a bag, you first reduce to this explicit substitution that has the whole bag with linear and unrestricted resources. And then you move to this, and then you split the explicit substitution in the linear and unrestricted part. And this rule is going to fetch the linear resources, and this rule is going to fetch the unrestricted resources, okay? We have a rule for fail. Let me see, this is interesting. So suppose that you have a term M that has, I don't know how many occurrences of X, and you have X here in the explicit substitution, but the size of the linear bag is different from the number of linear variables that you have. So we are going to fail. It means that your process, your lambda term, you have more resources or less resources than you need. You have to have a match between the number of resources and the size and the number of occurrences of variables. But this is the fail in the linear bag, okay? The failure in the unrestricted bag is when you want to consume, because the unrestricted bag is ordered, the index serves to say, I want to consume the ith element of my unrestricted bag. So if you go look at the ith element and it's empty, you fail. So there are two ways of failing. We type, so we have two different kinds of contexts, and one for linear resources and the other one for unrestricted resources. I think there's a typo. It should be somewhere gamma theta. So, right, we have two languages. We learn how to speak two languages. And we have to be like when you were a foreigner in another country, you have to switch between languages very naturally. So this is going to provide a connection between fail-prone programs and fail-prone interactive processes. It relates intersection types with session types. And it shows how non-confluence, non-deterministic functional behavior can be expressed in the pi calculus and preserve the same property. The translation is pink, is beautiful, but it's hard. So I'll just show one. So this says, if you want to, the translation of a lambda xm in U, so U is the name that you are going to communicate the translation of lambda x. So first to say, well, I'm confirming that I have a resource to communicate whatever translation of M is. So this is one example. But the interesting one is, how do we translate lambda terms to non-deterministic processes? So the part, if you remember one of the previous examples, where I had to choose between consuming elements of the bag, was when I was consuming, fetching in the linear bag. And we had renamed the occurrences of X with new names, and then the rule of fetch is on this. So there's lots of yada, but here, the parallel. Okay, so first here we are confirming that you have the names that you need to communicate, But here, this is saying, well, I'm going to permute all the names that appear here and see and consume them from the back. And this is translated to the pi calculus, okay? So another place where it appears is in the linear explicit substitution, because you have two bags and you have two ways of substituting these bags if you have two variables, okay? So this is the translation, like an excerpt of the translation. This is how we translate. We want to translate intersection types to session types. So we also had to provide a translation of the types. So this is how the translation of the types work. So an intersection type, sigma pi, is beautiful like this. And typing it by hand is very hard, and Joel suffered a lot because to type it by hand, we need someone to implement things to type for us. So, and just to finalize, to conclude, sorry, we want to prove correctness. What correctness? We want to prove that the behavior in the lambda calculus, reductions in the lambda calculus, after we translate them, we look at the reductions from the process and they have to be related. Okay, one has to be translation. That's what we get. Okay, so what happened is after we translated the term and we look at the processes, there was a mismatch on the processes that we obtained. So we had to define this precongruence that says, well, if I say P greater than Q means that P has at least as many branches as Q. So because of the mismatch, that's going to happen. So this is just what we have to prove correctness. So we have to prove that if there's a reduction in the lambda calculus, then there exists a process that there's a reduction from the translation of the lambda term to Q, and M, that's the result there, has as many or at least as many branches as Q. That's why we call BOOS, because in a previous work we had to find a lazy semantics where the relation that we had here was a structural congruence. It was one-to-one. It was a very nice, tight completeness and tight soundness result, but it was not what usually the pi calculus does for the non-determinism. So we wanted to have a non-deterministic non-collapsing rule because that's the behavior of the normal pi calculus. And then the soundness, and then what did we prove? I'm finishing. So we proved many technical results, type preservation and the block freedom in the pi calculus, subject reduction and expansion in the lambda calculus, normal properties that we need, and then the translation preserved types, and the correctness under the semantics that we defined. What means that I had to prove, Joe had to prove all the properties, all the lemmas, all the theorems that I showed. So just to finalize, so these semantics that we've defined, we call them eager. It means that we choose too soon, we commit too soon. Okay, and then all the three choices, if you remember the example that we made before, all the three choices are made in one step. So you make the example, the move server example, you choose one and in one step. Whereas the lazy semantics, you were going to analyze a bit, this reduction cannot happen, so I can discard this one between these two, which one I'm going to choose. The other one was more, it was lazier. And the translation that we have holds up to the congruence. So last year we had a paper with the lazy semantics that postpones the choice as much as it can, but it's very tight with respect that the semantics is tight between lambda and correspondence between lambda and pi. And then they differ also in the notions of pi simulation, not only in the operational reduction sense. Just to close, so we studied the relation between resource control and non-determinism in a type lambda calculus. So we introduced the two calculi that are non-confluence and non-determinism, both typed. Non-determinism is gradual and explicit. What else? Our lambda calculus is regulated by intersection types. We have a correct translation between them. So this just reinforces that the connection that we discovered between session types and intersection types is strong because we have explored different kinds of calculi using the same relation between session types and intersection types. And that's it. Thank you. Yes.
So you look at the non-deterministic choice as a cut, like you were typing.
Yes, it's a cut.
Session parallel composition.
Yeah.
For the card.
Yes.
What's that implication mean? This.
It's the communication. It's when you give one step of communication steps. Right? When you have a send and a receive parallel, one step of the synchronization between them. This is going to, the rule that's going to type this is the count.
I mean, I'm afraid I do not like very much of this section. So I was
But
wondering.
for us, it's how we are going to count the number of resources, and we use non-independent intersection types because it allows us to have many copies of the same thing. That's why we didn't find another way to do it.
Not even with your strips things, because, you know, I was about to ask for the previous work, for the 2023 work, because it seems to me.
It's the
latest
type
one.
system, the lambda calculus, the type system in the lambda calculus from the previous work was the same. Did you have to change anything, Joe? No, it's even the same type system. And when we were studying the confluent non-determinism, the type system was very different. I don't remember, it was 2021. I'm looking at Joe because he's the one that is the same as well. Yeah. So it's very stable, and then we can play with the language, and it's very stable for us. And what we do with the intersection types, we just say, know how many copies of a thing we have. So that's what we do with intersection types, with no independent intersection types. So here, for instance, let me see if I have put an extra room for. No, I didn't. Sorry. Oh.
No, that's true. I mean, there's some stage there that you put a bar.
Mm-hmm.
And I was kind of thinking to myself, what kind of bar is that?
Mhm.
You know, the upside.
Yeah.
Because
Yeah, but we have to think that our translation is from lambda to pi. Yeah, our translation is from lambda to pi. So there are many things in the process calculus side that there has no correspondence in the lambda calculus. We didn't prove the other way around of the translation yet. So there's Nobuko has asked me many times when we are going to do this, and then Joe finished his thesis, and we didn't finish the proof of the inverse translation. We didn't have time. Yeah.
no one else has, can I ask one more? Sorry. You're in a base on that. Go ahead.
Is there?
No, I thought it was,
Ah.
backing up with that actually, the sum there,
Mhm.
is it some sort of choice?
Yes. Yes.
Sure, that's it.
Yeah, that's good, it's a choice, okay.
I have a question.
Yes.
So lambda calculus is also new, or
Sorry?
because you proved the subject reduction, lambda calculus also you design or existing.
The subject reduction, we did have, it's because we couldn't show everything. It's like a huge work. So we have a type system, but we also have a well-formed, a system of rules to characterize well-formedness, because we found it was weird to have a lambda term that whose computation ended in failure and say that this is well typed. so we defined something that never failed, and we typed it with the type system, the intersection type system, but we had a relaxed version of the type system that allowed us to say this process failed, and I can give it a type. And then our subject reduction, we have one for well-formedness and one for well-typedness. And the expansion as well, right? Yeah, and the expansion as well. Yeah. Because we wanted to say, we wanted to be able to characterize failure. Because usually in the lambda calculus, if it doesn't work, you just forget about that branch, you just stop, it's a normal form, right? So no, but we wanted to be able to express failure and where it failed. Because here we can say it fails because I don't have the resource on X. We wanted to have something similar to lambda.
Okay, I think it's time for lunch now.
Okay.